All right, we're back. We're on page 9 of notes 14 of Calc C. The notes overall are about the logistic differential equation. The last page was just series review. This page, more review. Good stuff, though. I mean, this is where 5s on the AP exam are made. It's by reviewing. Like constant. You can't afford to forget anything. You want to try to see how everything fits together. Which, like, honestly, there's some topics coming up that don't really fit with the other things, but these do. So let's take a look. Function f is twice differentiable for x greater than 0. Okay, that's good, I guess. F of 2 is 20, given. F prime of 2 is negative 18. Okay. I don't know. And then the values of f prime are given for selected values. I have no idea what this problem is, where this is going. So let's see. F double prime. Okay. All right. Write an equation for the line tangent to the graph of f at x equals 2. Okay, so the tangent line, I need to know the value of the function. So f of 2 is given. That's 20. And then f prime of 2 we get from the table is 4. So it's going to be y minus 20 is equal to 4x minus 2. Use it to approximate f of 2.8. So f of 2.8 is going to be approximately 20 plus 4 times 2.8 minus 2. So 0.8, 20.8. All right, that's the thing. Use a midpoint Riemann sum with two subintervals of equal length and values from the table to approximate the integral from 2 to 2.8 of f prime. Use that to approximate or estimate f of 2.8. Oh, nice. Like, wait. Yeah, this is one of those problems. So it's like a type of problem where they ask you to do like everything you've ever done. So if you look at it, it's like approximate with a tangent line. Okay, we've done that. Approximate by approximating the integral and using the fundamental theorem. Okay, sure. Euler's method to approximate. Why not? Second degree Taylor polynomial. It's like all the ways of approximating a function. This is a really good review question. And also, I think it's modeled after an actual AP question. So be on the lookout, you know. All right. Integral from 2 to 2.8 of f prime of x dx is approximately, because it's only an approximation. So what are we doing? We're going two subintervals, midpoint Riemann sum. So if we go from 2 to 2.4, that's 0.4. And then the midpoint is here. Whoops, you're not a pointer. Is here, so the height there is 10. So 0.4 times 10 plus, we go from 2.4 to 2.8, that's 0.4. And then the midpoint is 2.6, and the height there is 15. So this will be 0.4 plus, nope, 4. Get out. 4 plus 6, right? So yeah, because 10% is 1.5 times 4 would be, yeah. So 10. And then we need to use this to approach 10? 1.5, that seems really big. All right, so then based on this, we're going to say f of, is there something like not right about this? Oh yeah, what is 0.8? 0.8 times 4 is 3.2, so this is 23.2. It just like the answers seem so, they don't need to be like close, like it's all estimates, so it could all be wrong. They seem like way off, and that was a problem. So if I do the integral from 2 to 2.8 of f prime of x, that's going to be f of 2.8 minus f of 2. So f of 2.8 for us is going to be, I mean, it's actually equal to f of 2 plus the integral from 2 to 2.8 of f prime of x. That's like its actual value. But this is going to be approximately the 20 that we were given plus 10, which is 30. So tangent line gave us 23.2. This Riemann sum approximation gives us 30. We have no idea. I mean, like anything could be happening. Euler's method with two steps of equal size. All right, table. This is a good problem. If you're struggling with any part of this, head back to the notes about, you know, all of these parts. F prime of x, y, delta x. So the step size is going to be, so we're going to go 2, then 2.4, 2.8. The initial y value is 20. That's given, unless I'm messing that up every time. So this will be 0.4 times the derivative at 2. The derivative at 2 from the table is 4. So this is 1.6. So we add those, we get 21.6. So then we're going to do 0.4. The derivative at 2.4. So 0.4 is the delta x. The derivative at 2.4 is 6. So this is 6. So that's 2.4. So that's 23/24. So we would say that f of 2.8 is approximately 24. So we now have a third estimate. So 23.2, 30. 30 is actually starting to seem like the craziest one. I don't know, whatever. Second degree Taylor polynomial. So the second degree Taylor polynomial at 2 is actually the Taylor line, the tangent line with like an extra term. So we're going to say f of x is approximately the value you start with, which is 20, plus the derivative at, like, it's 4, right? The derivative at 2, yeah. And then we're also told f double prime is -18. So that we're going to use. So it's f prime, which is 4, x minus 2. I was going to write to the first over 1 factorial. And then minus 18, x minus 2 squared over 2 factorial. This is the second degree Taylor polynomial. And so f of 2.8 is approximately 20 plus 4 times 0.8, which I've already gotten wrong once, so that's good. Minus 18 over 2 is 9 times 0.8 squared. I really don't want to do this by hand. 20 plus 3.2, and then it's so it's 64, but then 2 decimals, 0.64, so 64 times 9, I don't know, is 5.576, 5.76? I'm gonna say 5.76. I don't exactly know where I got all of that from, but so this is 20, all right, 23.2 plus 5.76, 28.96 potentially is my, so f of 2.8. I should check that one on a calculator, so let me do that. I mean, you don't really need to watch this, but I'm gonna do it anyway. 20 plus 4 times 0.8, let's just confirm that, yeah. And then minus crud, I definitely got it wrong, minus 9 times 0.8 squared. Let's just, for vanity purposes, add it and see if I got that. Plus 9 times 0.8 squared, 28.96. So had I done it right, I would have gotten it right, but I was supposed to subtract it, and therefore I got it wrong. I'm going to do some change-ups with different color. So when I flip back, you'll be able to see what happened. Okay, so minus, so it's 17.44, 17.44. That's so disappointing. So, like, I don't know, what's the truth? You know, what's the actual value? I have no idea. There's not enough information to really determine anything. Which of these is the most accurate? I don't know. I have no idea. But all of them are valid ways of approximating it. They all give you some pretty different answers. The one I'm the least comfortable with is 30. I feel like 30 is like way out of the ballpark, but I don't know. It could be right. Unless I totally did it wrong, which I don't think so. So actually, I think I did do it wrong. Maybe. Oh, nope. I think I didn't do it wrong. I don't know. All right, I think it's good. And it's just a surprising answer. Let me know in the comments. All right, I'm gonna end this. I'll see you in the next one when we're doing some new notes. So see you there.